All right, everybody, welcome back. Got a little bit of extra time here, so we are going to actually do, again, I'm going to do a quick overview of variations, a variation, I should say, for Chapter 8. So there's three types of variation. First one is direct variation. Just reading the definition here, a variation or proportion is used to describe relationships between variable quantities. K is a non-zero real number called a constant of variation or constant of proportionality. Okay, so a lot of times we're going to be solving for this K value in our equation. Okay, so here's your three types. Direct, inverse, or combined or joint variation, where it can be both direct and inverse. All right, you can see how each of these are formed and the wording used. Y varies directly with or as x, okay, is written like this. Y varies inversely with x, okay. So whenever you hear the word inversely, that's what goes in the denominator. And then jointly as x and y, everything's up top. But if it says inversely as y, that goes on the bottom. All right, so we'll talk about a couple of these situations. We'll go through a few examples of each, and then that'll be it. All right. So, T varies D varies directly as T. So D equals KT. And again, notice all these, the K is always there. Okay, it's always up top. P varies directly as the square of V. So P varies directly as the square of V. So we got to do V squared. The distance D that a free-falling object falls varies directly as the square of the time that it falls. So that's KT squared. All right. So the rule of thumb here when solving these is you're going to be given information in the problem. You're not going to know enough to know, or you're not going to be given K, your constant of variation. You're going to be given your other variables. So you're going to plug in your other conditions. The first step is write the general formula. Then you're going to plug in what you know to solve for what you don't, okay, which is going to be K. Then you're going to plug K back in, and then plug in what you know to solve for what you don't. All right? So, here's our first example. Okay, the price P of a diamond is directly proportional to the square of the weight. Okay, so there's step one. Step two, plug in what you know. Okay, so if a 2-carat diamond, that's the weight, costs $1,800. Okay, we're going to plug in what we know to solve for K. So I'm going to divide both sides by 4. Okay, K equals 450. Now I'm going to substitute K back in. I'm going to plug that in right there and rewrite my rule. And then answer the question. Find the price of a 0.7 carat diamond. Well, 0.7 goes in for W. All right, so we crunch that number. And we get $220.50. Okay, let's try another example. Okay, suppose you drive a car 392 miles on 1 tank of gas. The tank holds 14 gallons. The number of miles traveled varies directly as the number of gallons. All right, so there's our equation that relates the miles traveled to gallons of gas used. Okay, you only have enough for 4.5 gallons of gas. How far can you go? So let's plug in our fact here to solve for K. Okay, isolate K, 28, and then substitute that back in to your original. Gallons. And then 4.5 gallons, substitute in for G. And crunch the number, 28 times 4.5 gives you 126 miles. All right. So same fact here. Okay, so we can reuse our equation here. You drove 8,000 miles last year. How much gas did you use? So now we're plugging in 8,000. Okay, let's write our rule here. M equals 28G. So 8,000 goes here. And now we're solving for the number of gallons. So 8,000 divided by 28 gives us 285.7 miles. Or, excuse me, 7 gallons of gas. Okay, so you could do that. You could figure out how many miles each year you drive, multiply, or figure out how many gallons of gas you use according to your miles per gallon, and then multiply it out to the price per gallon, and it's almost depressing to figure out how much money you spend in fuel alone each year. Okay, but that's almost a necessity these days. There is another method to solve, okay, just using proportions. Again, you can do it quickly, efficiently, and easy. There's nothing wrong with substituting in what you know and solving for what you don't. I mean, that's pretty much the definition of algebra. But if we take our equation here, all right, we solve for k, and then if we know our second set of conditions, which is why it's subscript 2, all right, we know that k equals that and k equals that. So you just set those two equal to each other, cross multiply and solve. All right, so here's one example. If y varies directly as x and y equals 6 when x equals 5. So there's your first fact. That's x1, y1. All right, and then find y when x equals 15. So that'd be y2, x2. Set your proportion up. Y's over x's, cross multiply and solve, and we can get it. Okay. If we do it the other way, the first way, substitute in, solve for k, plug k back in, plug in what you know, you still get 18 both times. All right, so there's work you can look through. All right. If we look at the next one, again, y varies directly as x. We can do this one with proportions if you want. So we're going to do x's or y's over x's, so 9 over 8 equals y over 12. Cross multiply and solve. We get 8y equals 108 divided by 8. And there's your answer of 13.5. All right. Or, okay, you can do it the original way. Okay. X equals 8, y equals 9. Solve for k. So we divide by 8. We get 9/8 equals k. So y equals 9/8 k, or excuse me, 9/8 x. And then find y when x equals 12, so plug a 12 in there. And we get 13.5 again. Okay. So pretty simple stuff here. And again, what does a graph of something that's directly proportional look like? Okay, it's a straight line, has a y-intercept of 0 because there's no plus b on the outside, and your k value represents your slope. Okay, so the slope of the line, 3, constant variation, which is k, 3, they're equivalent. All right. All right. We can apply this to real life situations. Again, like we did earlier, here's a situation. This one's worked out. I'm going to let you guys look at that one. Again, I don't want to waste your time with such easy work. So if you want to do those, there they are. Okay, inverse variation is the second type of variation. All right, which is this one. All right, so now we're dividing by x. Okay. So what we have to have here is k cannot be 0. Okay, that's the only condition here. because then we have 0 divided by x, which is y equals 0. It's a horizontal line. It's the x-axis, actually. All right, so it can't happen there, and obviously x can't equal 0 because that's a domain restriction. All right. So we can use proportions the same way if you choose to do it that way. There's the work to show this one. As we scroll down here, let's see. I want to get into more applications of it. If we do, let's just set this one up. So find x when y equals 27 if y varies inversely as x. So that's k over x. Okay, so I'm just going to plug in what we know instead of using the proportion approach. Here's your fact to solve for k. Yeah. So y is 45, k over 9. All right. And so we get 45 times 9, which is 405. Okay, you can cross multiply and solve there. So y equals 405 over x. So find x when y equals 27. So 27 equals 405 over x. Okay, we can cross multiply and solve. Get 27x equals 405 and divide by 27. And we get 15. Okay, so inverse variation graphs are hyperbolas. Okay, that's what this graph is called. Okay, so we have a vertical asymptote and a horizontal asymptote. But notice here, okay, as x increases, the y values decrease, and as x decreases, the y values increase. Okay, again, just some observations. Okay, so let's take a look at this one. The volume of wood in a tree varies directly. Okay, so we're kind of getting into the joint variation because we're combining some things. Okay, so the volume varies directly, so that's going to be multiplied on top with the height, and inversely as the square of the girth of the tree. Okay, so let's plug in what we know. Okay, according to our fact here, the volume of the tree is 144, and the height is 20 meters, and the girth is 15. We can use that information to solve for k. Height is 20, girth is 1.5, and then we square that. So we have 144 equals k, or 20k. Well, I'm just going to write k times 20 over 1.5 squared is 2.25. So instead of dividing by this fraction, I'm going to multiply by its reciprocal to undo it. On both sides, of course. 20's drop, 2.25's drop, and we get k by itself. And when we multiply this times 144, we get 16.2. So if we come back up here and we plug that 16.2 there, all right, what is the height of the tree if the volume is 1,000 and the girth is 2 meters? Okay, it's a big tree. All right, so same thing, I can multiply by the reciprocal. So 2 squared is 4. Do that in a different color, just to show the undoing step. So we're going to multiply by the reciprocal on both sides. So the 4's drop, 16.2's drop, and we can solve for the height. So when we multiply this out, we get a very tall tree, 246.91 meters is our units of measurement. That's a huge tree. Okay. So we already did one with, combined or joint variation. Okay, let's just practice writing a couple, and then we can, apply it to some real life situations. So V varies jointly as B and H. Okay, so that's K, B, H. All right, remember, inversely, whenever you see inversely, that goes in the denominator. P varies directly as the square of V and inversely as R. The volume of gas varies directly as the temperature and inversely with the pressure. And the distance a free-falling object falls varies directly as the square of the time squared, that it falls. Okay? All right. Okay, 2 problems to go. The pressure P of a compressed gas is inversely proportional to the volume according to Boyle's law. Okay? So we got a constant of variation and inversely proportional to the volume. Pressure of 40 pounds is created by 600 cubic inches. That's your volume. Okay, and we can solve this. So we get 24,000 equals K. Substitute that back in. And then find the pressure when the gas is compressed to 200 cubic inches. Okay, so we don't know what P is. Okay, so we get pressure of 120 pounds per square inch. All right. Okay, here's one here you can try. Make sure you work it out. You should get 80 pounds per square inch. All right, you can try that one on your own. And the last one here, the electrical resistance R of a wire varies directly as its length and inversely as the square of its diameter. Okay, so plug in what you know. Here's your fact. So 1,000 foot long, or 100 foot long, diameter of 0.01. Okay, we're going to square that with a resistance of 25 ohms. All right, so if we multiply by the reciprocal, okay, that cancels. We can find our constant of variation, which is rather large, 25 million. All right, substitute that back in. And then plug in what you know. So the resistance of find the resistance with the diameter of that and a length of 50. So make sure you do the numerator first, and then, whoops, I forgot the square here, divided by the square of the diameter, and you get 5.55 times 10 to the negative 12, and our unit for resistance is ohms. Okay? So again, basically variation comes down to plugging in what you know to solve for what you don't for the constant of variation, and then to find the missing part, plug in what you know again after you substitute your K value back in and solve for your unknown. Okay, pretty simple stuff.